get started. We're looking at derivatives of polynomials and exponential functions. And essentially this one right here is we're looking at some different shortcut ways to find derivatives. The first one is we're going after polynomials. And so if you have just a constant function, so here this is like where you've got like basically, so this function here is just a horizontal line. And so the slope is 0 everywhere, so the derivative is going to be 0. And then this one right here is if you're taking a derivative of x to the n, then you bring the n down and then reduce this exponent by 1 to n minus 1. And this one, if you look at the definition of the derivative, you can see why this would be the case. It's basically the maybe I'll just show you guys. So its limit as h goes to 0. So if I'm taking the derivative of this, of x to the n, then I'm going to get x plus h to the n minus x to the n all over h. And then what happens is, limit as h goes to 0 of, what happens is when you expand this right here, you get x to the n plus n, x to the n minus 1 h. And then you get some other exponent, but it's x to the n minus 2 times h squared and a bunch of other stuff. And that's just x plus h to the n. And then you're subtracting s to the n. And so what happens is is that this and this are going to cancel. And then these h's are going to cancel, but every one of these other terms still has an h in it. And so when you take the limit as h goes to 0, this is just going to be n x to the n minus 1. Okay, so that's why they get that part. This is for when n is greater than or equal to 1, when that works. But then they were able to extend it. It's able to be extended to when n is just any number, any real number, where the derivative is just going to be that. Even when n is 0, because like technically this one right here, this is c is actually c times x to the 0, so it's really just c and the derivative is 0. But that's like bringing a 0 down according to this rule, and it's going to be 0 anyways. And then this rule here is basically if you're multiplying, multiplying by a constant. It's like if there's a constant out in front, then that's just going to come outside the derivative. So the derivative of some constant times a function is equal to that constant times the derivative of the function. And then here it's just like if you're taking a sum or a difference of two functions and you're taking the derivative, then it's the same as, then that's going to be the derivative of the derivative of the first one plus the derivative of the second one. Okay, that's if these all exist, by the way. Okay, so yeah, so that was a bunch of rules. And so then using all of these, then basically you can take the derivative of any polynomials. Like for example, if you had 3x to the 4th plus 10x squared plus 5x minus 23 pi. Okay, then you just basically, okay, you think of the 3 as being separate, okay, and then you do this rule here where you bring the 4 down, and so that's 4 times 3, that's just 12, and then x cubed. So that's the derivative of that part. And then you take then you add the derivative of this one, which is bringing the 2 down, so that's 20. And then x to the 2 minus 1. 2 minus 1 is 1, so it's just x. And then this one is 5x to the first power, right? So you when you bring a 1 down, and then it's x to the 0, which is just 1. So that turns out to be 5. And then the derivative of that's 0, okay? So that's an example of taking...
Sorry, I just have a quick question. So on that proof over there, I get the rule, but how did you cancel out the h's? There's the h squared over and all of that over h.
Yeah, so first of all, these canceled out, right?
Uh-huh.
This has an h, that has an h squared. The next term is going to have h cubed. Okay, so if I factor an h out of what's remaining, so if I factor an h, so you have to think that this and this are already gone. Those are gone. And then you think, okay, if I factor an h out of what's remaining, then I factor an h out of there, I factor an h out of here, but there's still an h left there. And this has, the next term is going to have h cubed, and so that will be reduced to h squared. Factor the h out, and then cancel that with this bottom one. And then set h equal to 0, but there's still h here, and there's h's in all the rest of the terms, so those all go to 0 as h goes to 0. And so you're just left with just this piece here.
I see. Okay. It's because the limit is as h approaches 0 that those cancel out.
Yeah.
For those extra terms.
Yeah. So just do all the canceling first.
Yeah. And so the first h gets factored out, and that cancels out the h in the denominator, and then the rest of them just becomes 0, and so the other terms just cancel out. Is that kind of how that works then?
Right. That's exactly how it goes.
Cool. Thanks.
Okay, so bottom line is this is the shortcut, and this is how you would do a polynomial. Okay, so even if you have like it raised, even if it's raised to a weird power, like if it's raised to the 1/2, then you do the same thing. You just apply this rule there. You're going to apply this a lot. Okay, so that's polynomials. Now exponential functions. For exponential functions, this is E is, okay, the way that this textbook defines it is E, okay, E is the number such that the limit is h goes to 0 of e to the h minus 1 all over h is equal to 1. Now, with that definition, what happens if you define it to be that way, then what happens is when you're taking the derivative here, that's going to be the limit as h goes to 0 of e to the x plus h minus e to the x all over h. Okay, and e to the x plus h is e to the x times e to the h. So we can actually factor in e to the x out, and we have e to the h minus 1, okay, all over h. Now, according to the definition, right here, according to their definition, when h goes to 0, all of this is going to go to 1. Okay, and so that's just going to be e to the x. As h goes to 0, all that goes to 1. According to the definition, the way that they define the number e. Okay, so that means that the derivative of e to the x is just e to the x. It's the derivative of it itself. And so this is exponential function, and the slope of the tangent at any given point is equal to the value, or the y value on the graph at that point. Okay, so let's go into some homework. And okay, so let's go ahead and do the first one. Let's see, from the previous page, we said that it's defined this way right here. Okay, e to the h minus 1 over h equals 1. Okay, now this is this right here is like is an idea of how you would define that. So, oh dear. Okay, so let me go to, dang it. Okay, let me go to GeoGebra. Oh wait, let me explain the problem first, okay? Hold on a second. Let me go back really quickly. Okay, so we're supposed to find these two limits here. The limit is h goes to 0 of 2.7 to the h minus 1 all over h. And also the limit h goes to 0, 2.8 to the h minus 1. Okay, so now you guys already know probably that e, the number e is 2.7 something. So it's between 2.7 and 2.8. So you already know this last one right here, okay? But because e is defined to be, so this is 1, they're just showing you how a possible way that you could come up with e by doing this sort of thing. So what we're going to do is I'm going to put these two functions into GeoGebra. 2.7 to the x minus 1 all over x, and then 2.8 to the x minus 1 all over x. Okay, so let's go ahead and do that one. So GeoGebra. So 2.7 to the x minus 1 all over x. Okay, that's the first one, and then 2.8 to the x minus 1 all over x, and that's the second one. Okay, so they're looking for the limit as h approaches 0. So what you can do is just zoom in on the graph right here, and this one's recognizing that it's not, it's got a removable discontinuity there. Same thing with that one. Okay, because when x is 0, then the denominators there are both 0, right? So it says they want it to 2 decimal places, and so this is pretty much this one right here, the top one, the 2.8 to the x minus 1 over x. That is closest to 1.03, and the 2.7 is closest to 0.99. It's closer to 0.99 down to 1. So, okay, so those should be the answers for that. So we'll go back and put that in there. Oh, before I go back, let me do this. I'm going to just do this one. I'm just going to go e to the x minus 1 over x. And that one goes right through 1. So you can see the limit of that one is actually 1, according to how they defined it, how this textbook defines e. Okay, so that means that this one we said was 0.99, and that one was 1.03. And therefore, the e is between those two values. Okay, so here, let's do some differentiating of functions. And this one's a really tricky one because e squared, and so we just got done saying that the derivative of e to the x is e to the x, right? But that's when you have an x there, a variable. This is just the e squared. So this is actually just a number. So the derivative is just 0 for that one, okay? That's kind of tricky, but that's just a number there. Okay, this one right here, differentiate this function. Okay, so if it's in this form where it's factored out, then the easiest thing is to distribute this x cubed first. So it's x to the 4th plus 4, x to the 3rd. Okay, so I'm distributing x cubed into there, and then take the derivative. Okay, so with this first one, the 4 comes down, and this x is dropped by 1 to 3. Here, the 3 comes down. 3 times 4 is 12. And then this is dropped by 1 to x squared. Okay, so that's going to be the answer to that one, and that's the answer to that one.
Wait, I'm sorry. Why was e to the 2? Why was f prime of e to the 2 0? Wouldn't it be 2 times e to the 1?
Because this is just a constant. So if you put it in your calculator, this is just going to be a number. Okay, so it's along with right here, the derivative of any constant is 0.
I see.
Okay.
Mm-hmm. I got confused because when I look at e, sometimes it reminds me of like a letter as if it were like an X, and I think that's what I was thinking.
Yeah, that's fine.
Thank you.
A lot of people, it can be confusing. Okay. So number 4. Here, the best thing to do here is to rewrite it as r to the -3. Okay, so instead of 2 over r cubed, it's 2 times r to the -3. Okay, and then the derivative, you just follow the polynomial rule. So this -3 comes down. So it's -6. So -2 times 2 is -6. And then this r reduced by 1, -3 minus 1 is -4. And that would be acceptable. You could also, if you wanted, you could put it in like this. I'm sure it would accept either of these answers probably. Okay, number 5. Okay, so here we have y equals 2e to the x. Okay, we'll get that in a second. Okay, this one right here is really weird. So it's really, the cube root of x is really x to the 1/3, but it's in the denominator. So that's 7x to the -1/3 is what we're looking at. Okay, now y prime denotes the derivative of y with respect to x. Here, it's 2e to the x, right? And we said the derivative of e to the x is just itself. So this is just going to be e to the x itself. Okay, so that's the derivative of this is just equal to itself. You can put any constant here, and that constant will just come down here, and the derivative be the same. Okay, here a -1/3 comes out. So -1/3 times 7 is -7/3. Okay, then you reduce this by 1. So -1/3 minus 1 is -4/3. And that's going to go here to -4/3. Okay, so this answer should work for number 5. Any questions as we go on? Please just stop me if you don't understand something. Okay, number 6. Here, whether you're talking about x's or some other variable, like here it's r, it doesn't really matter. Okay. Your independent variables are capital R. So it doesn't really matter. So you treat that as if it was just an x. So that's like x squared, right, which is a polynomial. So that means take the 2 down. So you're going to get 4 pi, and then times r. 2 minus 1 is 1. So 4 pi r. An interesting thing to note about this one is check this out. you know that the area of a circle is pi r squared, right? And if you take the derivative with respect to r, you get 2 pi r. Okay, so, but what is this on a circle? You know, this is the area. This is the circumference, right? Okay, so that's not by mistake. That's natural, which we'll talk about later someday. So the derivative of the area of a circle is equal to its circumference. Oh, that's interesting. Okay, so let's go to number 7, differentiating this function here. Okay, so what you have to notice here is that e to the x plus 2 is actually e to the x times e to the 2. So I'll put the e to the 2 there, right? That's just that. So x plus 2 is this. E to the 2 times e to the x. And then we have this 7 right there. Okay, so now when you take the derivative, this is just a constant. Okay, so it's going to be, the derivative will be this times the derivative of this part. And the derivative of this part is just e to the x. And the derivative of this is just 0. Okay, so, but then nobody leaves it written like that. So you rewrite it as e to the x plus 2. Okay, let's move along to number 8. Number 8, we're supposed to find an equation of the tangent line to this curve at the point 1, 1.
Just a quick question.
Yeah.
So for whenever you're taking any e to whatever number that is, then even if it's like x plus whatever, then it's always just going to be, basically anytime you take the derivative of e to whatever, it's always going to be e to whatever it is. Like you can essentially leave it alone. If it was e to the 1/2, would you?
E to the what?
Okay,
so there's like. Okay, let me try to answer that really quickly. The answer is no, because, well, we already know that the derivative of e squared is just going to be 0, right? So we don't, that doesn't hold there. If it's, so we'll be learning what's called the chain rule later on. So if you take the derivative, let me just say this, if you have some function f of x up here, so it's just some function of x, then the derivative is actually going to be e to the f of x times the derivative of the function up here. This is by the chain rule. So when we're talking about, when we get into how to handle compositions of functions, then this is what happens. So in this case, what happens is the derivative of this x plus 2 is just 1. So so this part right here was just a 1 right there, which doesn't make it, which doesn't change it at all. Okay, but if you have like, and if you did something like this, if you apply this kind of thing to here, then your f prime of 0 is going to be, then your f prime is going to be 0. Okay, so that's going to be 0.
Yeah, so that's what I was wondering, just because, so if the derivative of e to the 2 is a constant, that's 0, then wouldn't it be 0 times e to the x for the, which would just then be 0 for y prime?
Okay, well the f prime here is 1, because the derivative of x plus 2 is 1 plus 0, so that's just a 1. So like if you had this right here, let's say you had e to the x squared, okay, that derivative is going to be e to the x squared times the derivative of x squared, which is 2x.
Okay, I see.
Okay, so let's go ahead and work on this one here. So you want an equation of the tangent line to this curve at the point 1, 1. So you notice that if you put a 1 in for x, you get 9 minus 8, which is 1. So you get a 1 back for y. So this point actually is on the curve. The point 1, 1 is on the curve. Let me see, where is it? Whoa, it's not in, what? Oh, here we go. It's, looks like about 1, 1 is right there. Over here, that's not even intersecting at 1, 1. None of these intersects at 1. So actually, even before doing the problem, this is the only one where they have a graph of the curve intersecting there, and then the tangent line's also right there. So this is going to be the answer to the second part. Okay, but let's actually calculate it. Let's actually calculate the equation of the tangent line. So this one, we're going to rewrite it in a form that we can easily differentiate. Okay, the square root of x is the same as x to the 1/2. Okay, so that's the best way to deal with that. Okay, now that means y prime, the derivative of this part is just going to be 9. The derivative of this over here, you have a 1/2 coming down. 8 times a half is 4. So you have minus 4. And then subtract 1 from this. So 1/2 minus 1 is negative a half. So times x to the negative 1/2. Okay, now what we're going to do is we're going to set x equal to 1. And set x equal to 1 right here. And that is going to be, so the derivative is the slope, right? So if you set x equal to 1, then we get 9 minus 4 times 1 to the negative 1/2. That's setting x equal to 1. And that's just going to be 5 because this is just 1. It's just 1 over the square root of what? It's 1 over the square root of 1, which is just going to be 1. So 9 minus 4 is 5. Okay, and so that means that our slope is 5. And so our equation of the line will be y equals 5x plus b. Okay, replacing the m with the 5. Okay, now we also know that it goes through this point here. So we plug in 1s for x and y, okay, because y is 1 and x is 1. And you get b is negative 4. Okay, so y equals 5x minus 4. That will be the equation of the thing. So you only put in 5x minus 4 though on Webassign. Okay, let's go to the next problem. Here we have the function x to the 5th minus 2x cubed plus x minus 1. Okay. Okay, so this is that function there. Okay, now we can calculate the derivative. Oh, we can just write the derivative right here. Okay, so the derivative of that is you bring the 5 down and then reduce that by 1 to 4. Okay, bring the 3 down, that's minus 6. Reduce this to a 2. And then this one is just 1 plus 1. Okay, so that's the derivative right there. Now, compare the graphs of f and f prime and use them to explain why your answer is reasonable. Okay, so this blue one is f prime, y equals f prime of x. And the green one is y equals f of x. So the green one is the original one. Okay, the derivative is 0. Okay, so this right here happens at these points right here. And at every single one of these points, you have a horizontal tangent when f has a horizontal tangent. And that's what happens. We've talked about this before, that when the derivative is 0, you have a horizontal tangent at that point. Okay, f prime is positive. So here, positive, that would be up here and up here. So everything that's above, all this place where the blue is above the x-axis, okay, when it's positive, f, so that would correspond to this part right here, and then from here to here, and then from here on up, right? This is where f is positive, okay? I mean, where f prime is positive, the green graph, the original f, is increasing. Okay, and then finally, where f is negative, okay, where it's negative, f is decreasing. Okay, so that would be all this right here, where it's decreasing. All that right there, it's decreasing. Okay. And these parts right here are true about all functions in looking at their derivative. Okay, so let's take a look at number 10. Here you want, it's a first and second derivatives. Okay, so you want to take two derivatives of that. So the first one, as before, so this is like x to the 1, right? So we bring the 1 down, that's 3, times x to the 0, which is just 1, so I don't even write it. Okay, now, then this next part is minus, okay, 4 times 7 over 8, that's going to be 7 over 2. Okay, 4 to the x, no. X to the, okay, 7/8 minus 1 is negative 1/8. Okay, so that will be the first derivative. Okay, now for the second derivative, that was just take the derivative of the first derivative. So you take the derivative of this. That first part's going to be 0, so we won't write it because that's just going to be 0. This right here, we have a negative 1/8 come down, so that negative will cancel that negative, and 7 times an 8, 7 halves times an 8 is going to be 7 over 16, and then negative 1/8 minus 1 is going to be negative 9/8. Okay, and so that will be the answer to the second part. Okay, number 11. The equation of motion of a particle, s equals t cubed minus 27t, where s is measured in meters and t is in seconds. Okay, so that's the equation of motion of a particle. Find the velocity and acceleration as functions of t. Okay, so the velocity is equal to the derivative of the position. So we just have to take the derivative of this. So we have a 3 come down. Three comes down. There it is. 3 minus 1 is 2. 27t, that derivative is just negative, is 27. So minus 27. So 3t squared minus 27. Acceleration is the derivative of the velocity, which is going to be the second derivative of the position. So take the derivative of this again. You get a 2 come down, make that a 6. 2 minus 1 is 1, so, but we don't need to write the 1. And then the derivative of this part is 0. Okay, so the velocity is this one, and the acceleration is 6t. Okay, part B says find the acceleration after 9 seconds. Okay, so A of 9 is going to be, you just put a 9 in for t. Okay, you just plug that into there. And so that's going to be 54. Okay, and then the last part says find the acceleration when the velocity is 0. Okay, so what's the acceleration when the velocity is 0? So what you have to do is set the velocity equal to 0. But we know the velocity is this one, 3t squared minus 27. So you set that equal to 0. That gives you 3t squared equals 27, which gives you t squared equals 9, or t equals 3. Well, negative 3 also works, but this is only for t greater than or equal to 0. So we're just going to go with 3, okay? And then it says, so this is the time when the velocity is 0. So the velocity is 0 at t equals 3. And so the acceleration is, okay, so you plug in a 3 for t right in the acceleration formula. The acceleration is 18. Okay, again, if there's any questions, please ask. Number 12. Okay, what we're supposed to do here is show that this curve has no tangent line with slope 6. Okay, so first calculate the derivative. That kind of walk you through this. Okay, so the derivative of this is just 3e to the x. The derivative of 7x is just 7, so plus 7. The derivative of this is, you can bring the 3 down, that's 24 times, and then x cubed, so you take 3 minus 1, that's 2, so 24x squared. Okay, so that's the derivative. Okay, now here 3e to the x is always greater than 0, right? Because it's e to the x is always, you know, taking positive number raised to a power. Even if you're raising it to a negative power, it's still going to be positive. It's still going to be a positive number, because if you raise it to negative power, that just means it's 1 over raised to the corresponding positive power. This is also greater than or equal to 0 always. Okay, so this part and this part are always greater than or equal to 0. This is greater than or equal to 0. This is greater than 0, because this can never be 0 even. So y prime is greater than 7, okay, 0 plus, okay, so greater than this, 0 plus 7 plus this. Okay, so the derivative is always greater than 0. Always. So it can never be 6. I'm sorry, the derivative is always greater than 7 is what this is saying. 7. The derivative is always greater than 7. So it can never be 6. Because 6 is less than 7, and the derivative is always greater than 7, so. Okay. So that's the answers to that one. Okay, let's look at number 13. And here it is. At what exact point on the curve is the tangent line parallel to this line? Okay, so first of all, what we're going to do is we're going to take this line right here and find what the slope of that line is. So to do that, we're going to solve for y. And let's see that. Take the 3x to the other side, and then multiply by a -1, both sides. Okay, so that means that the slope is 3, always. The slope's always 3, okay? So in order for this curve, if this curve is going to be tangent to this line, or if it's going to be parallel to this line, then the slope, you're looking for when the slope is equal to 3, okay? Okay, so we'll go ahead and take the, also notice one thing, if you take the derivative of all this, you get 3. Take the derivative of that, you just get 3, which is the slope. Okay, but it's always 3. Okay, so now let's take the derivative of this. Okay, so the derivative of the 8 is 0, so that's gone. The derivative of this part is just 2e to the x. And the derivative of this is -3. Okay, so what we're going to do is we're going to force that to be equal to 3. Because we want to force this to be parallel to this line. I want to find out where that's parallel to the line. Okay, so when you do that, then and then you solve for x, so that's 2e to the x equals, okay, adding 3 to both sides gets a 6 there. Dividing by 2, you get e to the x equals 3. And then taking the natural log of both sides, you get x equals log 3. Okay, so the first point here, the first value here is going to be log 3. That's going to be your x value. Okay, and then to get the y value, you have to plug it into the original. Okay, you have to plug this into the original one. So 8 plus 2 e to the, so for this x gets replaced with a log 3. And this x also gets replaced with a log 3. Okay, so all of this is 3. And so this is 6, so that's 14 minus 3 log 3. And of course, that goes right here. So there's log 3 comma this. So this is the x coordinate, this is the x coordinate, this is the y coordinate. Okay, so now I have to figure out which graph this is. And it's going to be a graph where, well, the slope's going to be 3, right? So you want to look for where the tangent line is 3. So it's not 3 there. This is horizontal. This is negative slope. This is 3. There could be 3. This is 0. So it's got to be this one here. If this is the only one that can possibly have slope 3. So it's got to be this. And then I guess this line right here, 3x minus 6, yeah, the y-intercept is -6, and it's got slope 3 apparently.